Hello students, welcome back to next session. It is very simple topic that we are going to discuss in this session, how this pH and TS diagrams are used in vapor compression refrigeration system or cycle that we are going to see here. So these are all the topics we have. Vapor compression cycle, in last session we have completed this. In this session we are going to discuss about pH and the TS diagram. pH is nothing but pressure and enthalpy diagram, and TS is nothing but temperature entropy diagram. Deviations from theoretical cycle. So this is the topic we are going to discuss now. Next we have subcooling and superheating. The effects of subcooling and superheating in the refrigeration in this vapor compression refrigeration cycle that we are going to discuss. Effects of condenser and evaporator pressure on COP. So this is another topic we are going to see. Apart from subcooling and superheating effects, we have effects on of condenser and evaporator pressure, multi-pressure system, low temperature refrigeration, cascade systems, problems, and we need two sessions to discuss more problems and equipments, types of compressors and condensers, and then we need one more session to discuss types of expansion devices and evaporators. So these are the topics we are going to discuss, students. And now we shall start the pH and TS diagrams. So pH diagram is widely used in refrigeration analysis because it represents the energy transformations occurring in the cycle. So energy transformation that is happening during all four processes in the vapor compression refrigeration cycle, that is clearly given or clearly represented by this diagram, that is pH diagram. pH is nothing but pressure and enthalpy diagram. It plots pressure P on the y-axis and enthalpy H on x-axis. So on P that is pressure on y-axis. So it is a two-axis diagram, and enthalpy on x-axis. The different processes of ideal vapor compression refrigeration cycle appears as follows. So this same thing we have discussed in earlier session, how four processes are taking place. The first one is compression. So compression is represented from 1 to 2. So from 1 to 2, isentropic compression. So here it is isentropic compression. So ideally it is isentropic compression. There is a little deviation from isentropic compression when it is applied in actual practice. That is actual TS diagram. That is actual pH diagram. Slightly differs. I will show you that. So here in isentropic compression, during compression process, what is happening is pressure increases and enthalpy also increases. So enthalpy is also increasing. So next stage from 2 to 3, it is condensation, heat rejection at constant pressure. So during isentropic compression, during compression process, the fluid, that is refrigerant, acquires more temperature. So that is rejected here at constant pressure. So phase change from vapor to liquid is happening here. So from vapor to liquid, phase change you can see in condensation process. So next is expansion. It is 3 to 4. Expansion through a throttle valve. Pressure decreases, enthalpy remains constant. So during this process, it is expansion valve, or it is also known as a throttle valve. During this process, the pressure decreases, enthalpy remains constant. So here next is evaporation. During evaporation process, heat absorption at constant pressure. So now the phase change is happening from liquid to vapor again in this during 4 to 1 process. So now it is in vapor. Now it is ready to go to compression. So during compression, the vapor only getting compressed. So here all three processes are happening cyclic manner. So these are the four steps happening in the vapor compression refrigeration cycle. Already we have discussed this in our earlier session. Now we are going to discuss its diagram, pH diagram. So this is pH diagram, students. So now you can see here pressure is drawn on y-axis and enthalpy H is drawn on y-axis. Now you can see this is the subcooled liquid region. So this is the critical point. This is very important point. So from where you can divide this into three regions. One is subcooled liquid region, and we can have this wet vapor region, and then superheated vapor region. So with respect to this critical point, so this entire diagram is divided into three regions. One is subcooled liquid region, and then we have wet vapor region and superheated vapor region. So from this critical point, so here we have critical pressure and critical enthalpy. So from here we can divide this diagram into three groups. Now you can see this is the constant volume. So this is like axis line, and this is the constant volume curves. So these are the constant volume curves. So these are all the constant volume curves, and then constant temperature. So now this is the constant temperature line. It is the constant temperature line, and this is a solid line. It is a constant temperature line. So now from here to here it is vertical line, and then it becomes horizontal line. Again it becomes a vertical line. So that is constant temperature line. Now we have constant entropy line. So these are the dotted lines, we can see, students. So these are the constant vapor lines, so entropy lines, constant entropy lines. So this diagram, there is a chart known as pH chart. So that chart is required to solve few of the problems. I will teach you that while doing problems. So now you can see here these are the constant temperature lines, and these are constant volume lines. So these are the constant volume lines, and these are the constant entropy lines. So these are this is the diagram, and these are the associated curves in the diagram. Next is TS diagram, temperature entropy diagram. The TS diagram represents the temperature T versus entropy changes in the cycle. It helps visualize the irreversibilities and changes in the entropy during each process. So now we can see the irreversibilities and changes in entropy during those four processes. So those four processes. Now we can see processes in TS diagram. So compression cycle, it is isentropic compression. Entropy remains constant, and condensation, it is 2 to 3. Heat rejection at constant pressure, entropy decreases, and expansion, it is 3 to 4. Isenthalpic process, here isenthalpic process where enthalpy is constant. So entropy increases due to throttling process. So due to throttling process, the entropy is getting increased. And evaporation, the heat absorption at constant pressure. So entropy increases here during evaporation process. Entropy increases during condensation process. Entropy decreases. Please remember this point. And during isentropic process, that is 1 to 2, the entropy remains constant, except the isentropic process, the except the compression process, the all three processes will have entropy change. So this is the temperature entropy curve. So TS diagram, you can see this is the compression. This is compression from 1 to 2. For 2 to 3, it is the conduction. So this is the condensation. So from 2 to 3, it is condensation, and actually it should be 2 to 3. In between we have 2 dash. It is nothing but the actual point. So this is the theoretical point 2, and this is the actual point 2 dash, and then we have 3. So 3 to 4 dash, it is the actual point, and this is 3 to 4, it is the ideal point. So 3 to 4, it is ideal expansion. So during throttling process we have 3 to 4 process, and 4 to 1 again evaporation. So these are the four processes taking place, and here during 2 to 3, it should be 2 dash to 3, it is uh, constant pressure, constant temperature, it is constant temperature, and from 4 to 1 again it is a constant temperature. And this is the superheated region, and this is subcooled region. So subcooled region, so from this point, critical point, we can divide this again into regions. So this is again a simple temperature entropy diagram. And here during this ideal cycle, if you see, this is ideal cycle 1 to 2, the entropy is constant, S1 equal to S2, but actually it is not happening in actual cycles. Actual, in practical situations, it goes in this line. So this is the line, and this is not actually isentropic process, it is actually there is a change in entropy. So actually S1 is not equal to S2, but in ideal cycle S1 equal to S2. So this is the difference between ideal and the actual cycles. So deviations from theoretical vapor compression cycle here, students. The actual vapor compression cycle deviates from the ideal cycle due to real world inefficiencies. So there are so many causes for this. So due to which we can see there is some deviation from ideal cycle to actual cycle. The major deviations include the non-isentropic compression. So as I said, 1 to 2, 1 to 2 dash is actual cycle, actual process. Ideal cycle assumption, compression is isentropic, no heat loss or gain, but what is happening is actual deviation is some heat is lost due to friction and inefficiencies, causing entropy to increase. So subcooling of refrigerant. So ideal cycle assumption is refrigerant leaves the condenser as a saturated liquid. So but what is happening here is some degree of subcooling occurs, improving the efficiency by reducing vapor content before expansion. So this is what happening here. So it is improving the efficiency by reducing vapor content before expansion process. So this is happening in during subcooling of refrigerant process and superheating of refrigerant vapor. And you can see here ideal cycle assumption is refrigerant vapor at the compressor inlet is dry saturated, but actual deviation, if you see, the refrigerant the refrigerant is slightly superheated. So refrigerant is slightly slow superheated here because superheating of refrigerant vapor and preventing liquid droplets from entering the compressor, improving the reliability. So that is the reason, and it prevents the liquid droplets from entering to the compressor. So if there is any droplets entering into the compressor will be spoiled. So that should be avoided. So pressure drops in the pipes and components. So pressure, there definitely there will be a slight cross sectional area changes occurs normally if there is a longer pipe or running pipes. There will be changes in cross sectional area, and if you see those ideal cycle assumption is no pressure drop occurs in the pipes or system components. So this is the assumption, while in the pipes there is no pressure drop, but actually the friction losses cause pressure drops in evaporator, condenser and pipelines, reducing system efficiency. So pressure drops occurs during the travel in these components, evaporator, condenser, pipelines, and ultimately it reduces the efficiency of the entire process. So heat exchange with the environment. Ideal cycle assumption, no heat loss to the surroundings, but actually some heat leakage occurs affecting cycle performance. So this is obvious if there will be heat conduction from one part or one component in the system to the surroundings. Definitely there will be slight uh, drop or slight heat transfer, that obviously occurs wherever you have this heat. And you can see the books. These are the reference books. CP Aurora is a very good book. You can refer for particularly for this topic. And refrigeration and air conditioning by Rajput. You can also refer this. And the RS Kurmi is a very simple book. You can refer this. Apart from this, we have few resources, online resources. Even you can rely on this. So this is the ph and ts diagram, and the causes happening due to various reasons we discussed here. So that is the deviations from ideal cycle to the actual cycle. So those deviations are all 2 mark or 5 mark questions. And the entire ph diagram, explain ph diagram or ts diagram with the deviations, it can be a 10-mark question, students. So you can prepare this. We stop here. We will meet again in next session. Thank you.